So I think we're back. We got Sherry responding true as a. I think you have a future computer science, Sherry, answering the question if you can open my cars logo. Answering true. Yeah, you have a future in CS, computer science.
I don't know who Sunny Shorty is. We also had Ryan Lee and Aaron came back in.
Okay.
But I haven't seen anybody since.
So, and you can see all the links I put in before folks came back in because we're in a new session. So I figured we have to put in. Okay, so you can see I put in a car model that I modified over the break just to. It's better than what's in NetLogo. Just like ants, I want to have two pheromones, but here I want to see the cars driving on the links. I don't want them just to jump to the next node, right? So you can open that and play with it. And I have Dr. Janecky's it's on there as well, right? And mine again.
Cool. Yep.
So let's just take a real quick look at the cars model that I posted up there. And you should be able to click on it and download it and open in NetLogo. And up my screen.
Thank you.
And I just want to kind of walk you through the logic. And it's really not, my intent is not like how do you do cars on a network, but it's really how do you think about when you're modeling in NetLogo or agent-based modeling in general, thinking from the perspective of the turtle or the patch and what it needs to do as it's doing its interactions, and not trying to model from the macro level telling everybody what to do, right? Just always think from the perspective of what does that turtle need to do, right?
Okay.
If you watch this, and again, double click on my shared screen if that makes it a little bit bigger for you. And so no, I'll slow down time. So we have a speed of the cars, and that's how much it's going to step every moment. And so basically these cars are moving, they're picking a goal. And if they get close enough to that goal, then they pick one of the outgoing nodes. So every node has links. And you can say, what are my outlinks? And getting the other node at the end of that. And that will be the goal for this turtle. So, and then how do you think they're staying on the right-hand side of the road? Anyone have any guesses in the chat?
And just type your answer in the chat. Ryan, if you figured it out, just tell him. I don't know if Aaron's got hers up or not.
It's kind of a cute hack of how to make it feel like they're on the right-hand side of the road. They're really going down the center of the link, but I'm drawing them on the right-hand side at all times.
Well, when they pass each other, they go on the correct.
Well, they can collide, but they have some. They're going to stay at least on the right-hand side of the link. Anyone? All right, so let's look at the tools and go into the Turtle Shapes Editor. And I'm going to have this on the right-hand side. And if I look at the code, notice that we set the cars. So basically we have cars. And a reminder, we have two kinds of breeds, nodes and cars. And cars have a goal, lane, and a speed. And they have a shape. That red triangle or chevron is car 2. And if I open up car 2, I actually draw the shape to the right of the center. So that's a little cute trick or hack to make it look like it's on the right-hand side of the road. So logically, the model isn't doing that. So if I ever needed interaction that it mattered, but this was more of a visualization hack, just so they look like they were moving on the right? And again, you can draw your own shapes in here and things like that. But I just want to show you the whole model here too. Then I'll expand the Control plus on Windows or Command plus lets you increase your text size or your viz size. So really, this is the whole program, right? It's not too long. And In the beginning, these are comments, all the gray stuff with the 2 semicolons or 1 semicolon. We clear everything. We make the default shapes for nodes and cars are circles in car 2. We create 70 nodes at the beginning. We make them blue and a certain size. And then we ask the nodes to create a link with one of the other nodes. So other just means not myself. So create a link with one of other nodes. And then there's this cute little repeat 500 layout. And layout is basically just a spring layout where we treat the nodes, the links as springs. And that layout spring function in NetLogo takes 5 parameters. Who do I want to lay out? The nodes along their links. And then this is how stiff is the spring. This is the natural resting length of a spring. So in a spring, when you get into physics, and many of you may, well, in the answer in the chat, how many people have taken physics? And what's our grade level here too? So answer your grade level and if you've had physics. So Aaron, yes. Alexis, yes.
Ryan. Saul.
Ryan. Junior taking it now. Good. And actually, I'm going to Google here. And you, it's kind of early, still kind of early in the semester. But have you guys taken about springs and Hooke's law? Oh, yes. Great. Yes. Awesome, Aaron. So basically, Hooke's law is a spring has a displacement force, right? So how much it's displaced from its resting length. So normally a spring that doesn't have a weight on it has a resting length. And then if you displace it, if I push in, it repels out. It wants to go back to its natural resting length. Or if I pull it out, it wants to come back. So it's a positive or negative force. And how stiff that spring is that K. And this, even though we're talking about springs, this is a great interaction law. Like I talked about, agent-based modeling has interactions, and we've already talked about 2, the gravitational law, right? These are forms of interactions. We'll just look at the gravitational equation, which you may have had in physics as well already, where this is, again, there's a constant in here, just like the K in Hooke's law. Let's see if they show it here. Yeah, so here's the classic gravitational algorithm, where it's 2 masses, mass of one body or agent times the mass of the other agent divided by the distance between them squared. And then G is a constant, right? So we were doing that not just for bodies, but for populations, if you remember, with cities and the probability of transitioning between cities. So the point is that these interaction laws, even though it's in one discipline, may have a similar form in another discipline. And so, so this spring is also how we lay out our networks, right? So as I come back to here, so if I did it, so this is what's actually laying out the springs, and the last term is a repulsion to make sure they spread out, right? And if I didn't do that in the beginning, basically all the nodes would be in the center, right? So this layout spring, I'm reporting 500 times. I was doing that, and maybe I'll show one that's more interactive. But I just want to, for the cars bit, we're laying out our network that way. We're asking the nodes to set in the beginning to spread themselves out as well. I'm surprised that we're, basically, if you read this, it's been a while. I just didn't want them on the very, very edge, so I'm scaling them down by 0.95, so they don't go all the way to the edge and wrap around, right? They're circles. And then we're going to create 25 cars and set their goal to be one of the nodes. So that's where they want to go. And in the beginning, we're going to move to their first goal. And then when we drive, we're going to say the go is going to be ask all the cars, if the distance to your goal is less than half of a patch is always 1 in NetLogo in size, then choose a new goal. But and if and go forward, then your average speed, which is a slider value here, like go 0.06 the width of a patch every time step. Okay? And to choose a new goal, like if we get to an intersection or we're within half of a patch of an intersection, we're going to make a new goal. One of the link neighbors of the goal is the node, and link neighbors, because they're on links, is one of the other friends, basically, or link neighbors along the link. And we'll set the lane to the link with the new goal. Now, we're not actually using the lane in our logic, but in the future, you could have, like looking at the density there, or but we're not actually even using this lane right now. So once we get a goal, we just face it. So really, this turtle doesn't know anything about the links. It's really, as I said, piecewise linear lets us just say, go look at that new goal and now move toward it in increments until you get close enough. And then, this comes into play again, choose a new goal. And that's all we're doing, right? And this is the average speed of the cars, so we can go really fast. And by the way, speed is always just a scalar or a number. Velocity usually has a direction to it. So this is just, we're not telling it what direction it's going. We just care about its the magnitude, right? And notice that this is just a good first approximation. Notice they turn around and potentially with some probability at every node, even if it's in the middle of the gyroscope. That's the beginning of a random walker on a network. And again, this could be many things if you can express, sometimes with a raster, sometimes a vector, and sometimes you want to express a lot of systems as vectors of things moving on it. And you can express gradients on here as well, just like we do with the raster of like when I showed the Zozobra model, when you come to this, imagine you were able to flood fill. And by that, I mean, I just march along and counting the distance. Let's say I wanted to get to here, right? And I want to do routing. And so what I can do is flood, meaning like I can take what's 0 and then make this guy 0 plus the length of this length. This guy is that plus this. This guy would be this number of distance from here plus that. So this guy's like further away, right? So if you keep flooding the values and holding it on the nodes, so when this car is driving and needs to get, it just goes, looks at the neighbors and goes to the shortest number or the smallest number, and there's now a gradient on a network. And that's a very powerful thing to do in routing, right? And I'll just show you an example in a real world when we apply this. It's going to go to what runs on our sim table in GIS. And you guys can help me here too. We're going to do another QR code example. And so notice we're running this in the browser. We call this any hazard. And if we put this through a projector and shine it onto a sand table. And then we have a camera watching the sand table to make it interactive, like a laser. Right? But I want to show you how we use what I just showed you in modeling traffic and routing. And think of when we talked about how light wants to find the shortest time path. Well, a lot of things in operations research or in physics, you want to find the least action path or least effort, which you can think of energy times time, right? So as this is coming up here, so think about I wanted to route from my house to the airport. And what is that path I want to take on the network here? So I'm going to choose a different scenario here. Oh, I think I already have it running here. Let's see. Here we go. So I'm going to bring up a model here in Albuquerque. Here we go. So this is, if I hide the elevation, this is I-25. and I-40. And this is to Harris and the back way to Madrid coming up here. And this is also pointing out that as you go and learn this stuff in NetLogo, you can also move that over to JavaScript running in a browser. And so I just want to show you the different things that we showed. So the first thing would be I could bring in the elevation, and for your project, then we can color the patches based on height. And then we can also just say make black lines along anything. If I had elevation, for instance, if I look at the elevation in Albuquerque, this is 5,600 feet, right? And this is 5,890. Well, what we can do is ask for every mod, we can mod that number every 100 and make it black. And that's how we can make the contours. And if we mod every 500, we can make it dark black, or mod every 50 or 100, we can make it gray. That's how you get a contour, right? And mod just means like taking the remainder. It's not technically completely, but it's kind of like the remainder, right? So here now we're going to do particles. As I release them on the hill here, and now we're building up a rainstorm. I can have it rain everywhere, and we're building up the hydrology of Albuquerque. These are the sandias here, right? And I can turn on Bing Hybrid. So all these. So the nice thing about the web is all of this data is available that we can bring in on the fly, right? And make a water model. And for Israel, this could be, we can have different layers of information. For instance, here, we can go to another site that gives us the vegetation class or the soil types, right? And that might tell us our turtle. At the end of the day, these are just turtles coming downhill looking at their neighbors. And they might flow faster, or if you think of the slope as giving them a velocity and the vegetation class or soil type creating a certain kind of friction or a different probability that you might percolate. Like an impervious surface like asphalt would have a 0 probability of percolation, whereas a sandy soil, you have a higher percentage, right? And you could do stuff with rain, pre-rain and post-rain events. So this would be another example. So what I want you guys to do now is, again, take a snapshot here with the phone. I don't know if this is big enough. I'll put this URL in the chat. And you can also bring it up on your browser in the here. So we're going to make a distributed simulation, or you can click on that link I just put in the chat and do it on your laptop in another browser, right? And so what I'm going to do now, so that's water. I want to talk about when we're doing routing. Imagine here's now in Albuquerque, and I'm going to hide my cars, my rain, and I'm going to turn on OpenStreetMap data, and I'm going to hide my fuels. So in this era, what's pretty amazing to me is this data is available almost automatically, in the sense that I can zoom to anywhere in the world, including North Korea or China, and get the road network and convert them to equivalent of turtles and links on the fly, right? So we can go get this, and these networks that you get from OpenStreetMap include the speed limits and the number of lanes here. So now you're going to see, as we're in Albuquerque, and I put cars down, I'm just going to brush them on here, brush some cars, or I'm going to bring in guys moving around here, network, right? And then from and now I'm going to put in a fire truck that needs to get somewhere, and this will be doing the routing. So let me. This is the routing that we talked about, where we're flood filling the network. So say this fire station is here, and I need to come over to Sandia Foothills open space, right? So as I put a car on here, you can see that it calculated the shortest time path to get there. And that is not the shortest distance, by the way. So it's capturing the distance, but also the speed limit to calculate the shortest time path to get there, right? And so that's an example. So when you guys just came in, by the way, so let me restart the model here. And I'm going to ask you guys to change the wind. So I'm going to put a hazmat plume. Now let's just say there was a chemical release here. Someone just is actually flooding a watershed. Someone else is doing that. That's kind of cool. And notice it's interacting with my world, right? So we're out of a remote simulation happening between us. So did you put down that calculate the watershed for that point, maybe? You can put it in the chat so you have to.
Stephen, I think we lost him for a minute.
Okay.
He should be right back.
Yeah. So someone did. Well, that's fine. But I'm going to reset that water model. And what I'm going to do is put down someone's starting a fire. You guys are already learning how to do this. That's fantastic. So to number 2. So what I want you to do is go back up to the settings on the top right. And a button, when you click on settings, you'll see on the bottom some tabs like weather. And click on the weather tab. My machine is running a little slow as I'm sharing the screen here. Some people are putting in evacuation areas. I appreciate that. And so I'm going to click on my settings here. And down on the bottom, you should see weather. And I'll let this come up here. This is running really slow. Maybe if I turn off my video. And what I want you to do is change the wind. And I'm going to put some smoke in here. I'm going to make a hazmat chlorine release. And now here is a simulation of particles that are randomly moving. And they're going to go with the wind. So they're going to be randomly walking around, but the wind is going to be biasing them. Every time step, it will also look at the wind and move them. So some of you are moving the wind right now, right? And someone just made a 60-mile-per-hour wind coming out of the east. By the way, in emergencies and weather, we report where wind is coming from, not where it's going to. So right now, someone's making it a southeast wind at 27 miles an hour. And so basically what you guys are doing is if I click on settings over here and get to my weather, so see how you guys are changing that? That's nice. And it's changing the simulation. And so this is just an encouragement of, yes, prototype in NetLogo, but think about ultimately transferring it to JavaScript in the browser. Because we just made a distributed simulation that also may not need to use servers. And there's ways of keeping our data private as we share the information and intel, but not our raw data. Like you could be tracking your location during COVID, but never giving that to the government or to Google. But you might want to contribute to your neighbors and your city to estimate where the infection is or the contagion. But we don't need to give all of our data to Google and the government. So this is like an example of a bottom-up system that we can make in New Mexico. If you think about this more peer-to-peer, where every node is a computer or a phone, and you treat them like turtles, and how do they interact? Notice in NetLogo, you learn how to make systems that don't have a central thing telling everyone what to do. So I'm glad you're learning computer science from that perspective, because when David and I grew up, we pretty much didn't learn it that way, and we had to learn how to make parallel systems. If that's fair, David, would you agree?
Yep, definitely.
Yes.
So well,
coming out of the gate,
you guys are program I wrote was on 12K.
Okay, so, but also, if you also notice here, let me just say one other bit about this. If we copy this event, and imagine we now go here. Imagine that same information being embedded on the news as it's happening and getting that out to the public. And this is happening live of what you guys are changing. Let me change this to this scenario. So this is the Tejeras Canyon scenario. And so as you guys are adding stuff on here now, like this chlorine leak or equivalent, that's changing. So I find that interesting. Oh, scenario equals. Here we go. So go ahead and change the wind, some of you, and you'll see you guys are changing the wind, and imagine the news now is changing because of that, right? So let's go think about one last, so let's go into NetLogo now and look at some of these, so we did fire, by the way, in here, fire, hazmat, water, and traffic, right? So let's think about how you would simulate these 4 kinds of things in NetLogo. Because they shouldn't be, the fact that you're doing them in parallel is what makes it powerful, right? So let's go ahead and open up our NetLogo again. And we're going to go into the model library where there's 2 GIS examples. And if you go to the models library here, and I'm going to close this guy for now, just to keep my computer running okay. And we're going to go in, when we're in the models library, we're going to go down to code examples, extension examples. So GIS is an extension in NetLogo where you can have other things. And by the way, other extensions include the ability to bring in video and live camera feed. So you can do machine vision in NetLogo. So you can bring in a webcam and like do object tracking if you wanted to learn about that, right? So there's ways of bringing in camera with using the video extension, or different things for doing sound, or or bringing in CSV files for data. But what we're going to do is bring in GIS. And the first one we'll do is a general, the gradient example. And if you, again, I'm in code examples, extensions, GIS. But if you had to find it too, by the way, you could just type gradient down here, and it would get you all the things that use the word gradient, right? And this is especially good for water models, that Israel's working on, but also in like a cancer cells, those things may be following gradients, right? And being repelled by things, or they're certainly moving. Their metabolism is faster than their surrounding cells, and their reproduction rate. So we're gonna. What this is gonna do is we hit
looking for an article.
Go ahead, David. Yeah.
So yeah, I was just thinking about the Aaron and Alexa's cancer stuff, and there was an article recently. I'll find it here in a minute. I think it was in Nature, but it might have been in Science, about how basal cell carcinoma is very sensitive to their substrate, and it's exactly parallel to these models that you were just describing, where depending on sort of the stiffness of the substrate and how the cancer cells affect that, it changes whether the cancer can even become very transportable or not. And so it's exactly the same sort of geospatial, just on a very small scale. And I'll find the article and put up a post to where that is. And certainly I've got a subscription, so I can grab the article for people if you don't have access to it. But it's going to take me a minute because I don't remember which version of the journal it was in.
And when I looked, David, so to me, that reminds me of what's called chemotaxis, right? So where a cell is following a chemical gradient, right? So I'm looking at basal carcinoma, substrate chemotaxis. Yeah. And I don't know this space at all, but it was just enough of a search term to kind of now look at what we're doing with water on gradients. You can think of how cells may follow a gradient. Like here's an example of a cell going up a chemical gradient, just like the ants, right? Or they're being repelled by it. So they measure the gradient and move away, right? And so you imagine there might be some kind of, why do we get clustering or clumping with cancer? It could be from reproduction, or it could be they could be aggregating, right? They could be, reproducing in one spot, and I don't know the
And that's
answer.
exactly
Right?
what
Clump?
this recent study was doing. Yeah. Well, in
Mhm.
fact, we're learning a lot
Yep.
about those sorts of problems. And this study was a very nice one, looking at both experimental work and theoretical modeling, and saying, well, if the subject was stiff, the cancer would move in one way. And I was intrigued with the spatial aspects of it, but it's not my area of expertise. So I read it and then went on and triggered the idea here that yeah, there's lots of interesting stuff on not only chemical but actually the actual structural basis of the substrate is important, and we're just starting to learn those sorts of things. So that's a great area for you guys to think about and work on.
So, okay, so inside the NetLogo, so notice I'm going to the manual here, the dictionary or the manual, and that's where we have all the primitives that you can look up how they work. And I would just really sometimes just read through a lot of these. As you click on them, it tells you how they work and gives some examples. But over on the left-hand side is the manual for the extensions as well. So in GIS, as we bring this up, it'll talk about bringing in raster. Both of they're data sets, and they're of two types, raster and vector. And what can you do with a vector, and what can you do with a raster? Well, for our water model, we're going to bring in a raster, and we're going to sample it and apply some, when a turtle is moving on it, it's going to look on a raster that is, every pixel has a slope and a direction. So it's going to face the direction and move based on the slope. And these rasters are derived from the elevation. So that's what is going to happen here. So when we look at this model, and I'm going to hide my turtles real quick. So basically every patch created a turtle. That's these blue guys here. But I'm going to hide them for a second. So the first thing is we're bringing in is a raster. This is a real elevation file. And to prepare for NetLogo, it takes two kinds of rasters that it can accept: an ASC file, which is an ASCII grid file, or a BIL file, which is a binary file. And these are very old standards that are that you can get any GIS file program to export to. On the web, we would use TIFFs or PNG or tiles, but start off in NetLogo, and we can get you the data in the format you need. If you want to learn that world of just managing data, that's also a very valuable job in the, and very. So there's two major programs you can use to do that. The free open source one is QGIS, and it's on all platforms. So this is, but like any open source thing, you sometimes have to do a little bit of work to manage the interface, but it's very very reasonable, right? And obviously free. And then the big gorilla in this space is called Esri, and this is a professional GIS tool. It has, I'm sure, if not free, highly discounted student versions. But it's almost like this is the Microsoft of the GIS world, and so this is where you can do that kind of thing. I've actually had some back and forths with the owner, Jack Dangermount, in his office about moving toward a more peer-to-peer GIS and browser-based instead of server-based. So, but anyway, check out ESRI and then QGIS. So now we're in here, and we brought in the elevation as a value. So if I inspect this patch has a location and a color. So that color was painted by the underlying raster. Now, just to make it clear, this patch system is only 80 by 80 with a center pixel of 81 by 81. But the underlying data set is at a much higher resolution. And when we come in here, this may look a little bit different for you. But whenever you use an extension, you have a GIS colon, the extension name. And whenever we use an extension in NetLogo, we declare it at the top, which extension I want to use. And that brings in all of its properties and methods that we can use. So one of them is set the world envelope, which is the bounds of our world, to the envelope of this data file, which we brought in here. So we're going to set our elevation to this data set, which is an ASC file, and it's in the data folder. And it's just a file that you can open up in Esri or in QGIS. And it's just a grid of numbers for every pixel, if you will, is the elevation. Now, this is very sophisticated and powerful. And what this is, and it's called convolutions, where every pixel looks at its, say, 9 neighbors, including itself, and samples from it. So there's 9 numbers in here of how much it samples from its neighbors. So this is a way that we can create from this elevation, what's the horizontal gradient, what's the vertical gradient, and then, as you know, and then also from that, we're going to create a, we're going to compute the slope as we put those two together. And I don't expect you to completely grok kind of what's going on here, but so basically we're creating these as these are ready to be putting values in it. It's not actually computing them yet, but when we do compute them, when we put it into the slope, we're going to use the horizontal gradient and the vertical gradient, and we're going to basically do like a Euclidean distance, which is right here. You know how you find the distance between 2 points? It's the square root of x squared plus y squared. So that's really what we're doing when we get a horizontal gradient and a vertical gradient. What's the total slope? And then what direction is the arctangent of the y and the x? But at the end of the day, we have the raw elevation and then 2 derived data sets, rasters, that are what's the strength of the slope and what's the direction. And then notice when the turtles move, all they do is they say, go forward some random normal amount. They're going to sample a normal distribution. And then they're going to sample the aspect and set their heading. They're going to turn to that direction. Aspect is what was the direction of the slope, right? And that's pretty much it. In fact, it's not even using the strength of the slope, is it? No, it is not. So it's really just how does it face and walk, right? And so when we also now show the slope, right now we're showing the height or the elevation. Here's the slope. So that's the intensity of the gradient, right? And then here's the aspect going from looping around. It's kind of hard to read, but what direction is it facing? And now when we show our turtles on here, we have a turtle in every spot here. And if I inspect this turtle here, or this patch, so this turtle, and if I just go once, I'm going to have it just go once. I'm going to observer and type go. These guys are all facing on their local gradients and stepping forward, and that's it. And having a particle move on a field that you calculate a gradient for, the slope and the aspect, is so powerful in science. It's pretty much every discipline you can think of modeling it from this perspective. All models are approximations and all models are wrong. Some are useful, but there's so many times where modeling particles on fields applies, right? So even though we're just doing this for water, so I'll step this one more time. And one of the things I like to do is also I'm going to ask the turtles to put their pen down. I can track their history, right? So if we let this go, that is the hydrology on this network, right? And so also there's always, whenever we do modeling on gradients, you can always go the other way, like go uphill. And I leave it as a challenge for you guys to change this model. And instead of going downhill, go uphill. And what do you think you would find if you modeled this to go uphill instead of downhill? Right now, we found the rivers, right? The drainages, just visually, and the population of where the turtles are. What do you think if you started the turtles off randomly and went uphill? What do you think it would be? Reach the top of the mountain. Yep. So reach the top. Not only the top, what would be because we're finding the bottom here, right? But along the way, we're finding the drainages. What do you think, Ryan? So yes, you'd reach the top, but along the way, and how could we, I haven't even thought of this. How can we change the code? If we're going, find the aspect, set headings, subtract headings, H180. So once he does that, I'm gonna have him turn 180. And I think that'll do the same thing. Set up, go. And as they do that, by the way, let's pen down them and go. So we just inverted the model and ran it backwards. So basically, Ryan, you're right. It got to the top of the mountain, but along the way, it found all the ridge tops. Right? And sometimes, if you remember how we did a watershed, if I want to think, a watershed is all the points that something drains into. You can run the water model backwards and drag it out and say, here's where my watershed is. And I think it's very important too, when you think of, we just inverted what we call inverting a model and running it backwards. I think when light finds least time, it runs backward in time and forward in time. And you have the algorithm changing of how it's propagating as a wave. And then when those two waves meet, just like the ant system, it solves the problem. Just like when we were routing, by the way, I didn't go too far into the fire trucks, but we started the destination and flood fill back from the destination, and we flood fill forward from the origin. But when we flood backwards, we have to flip all the lanes so that they go, because you have a lot of one ways, so you have to flip them. And that algorithm, I think, is the most fundamental algorithm in science of how we call it bidirectional path tracing. We think it's more important than natural selection of how systems transport energy, and so many, or mass, or any kind of field of energy. So it's speculative, but I'm just kind of telling you what I'm interested in. And I could have nice active discussions with Dr. Janecky about that, right? But anyway, you're seeing us fighting the ridges here. Right?
Definitely.
So this was a wrap with point turtles. We have points, as the turtles are vectors as points, and they're coming uphill. But let's go ahead and do one other one here, which is the standard, which is general. And again, it's in sample model or code examples, GIS, general examples. And this just shows you bringing in a shape file and all the different ways. And you can go look on the hard drive, your hard drive, of the different files that come with a shape file. And that was an Esri proprietary format. And you know, in the modern web, we tend to use not shape files, but KML or GeoJSON. JSON is like stands for JavaScript serialized object notation. So on the web, or in the 90s or 2000s, we'd use XML. But on the web, it's pretty much KML and GeoJSON for your vector data. Right? But anyway, this is using a shape file. And if we set up the world, you can see basically it's going to assign vector properties of the data set to like displaying the rivers in the patches. And you can see that we got really low resolution patches, right? Or we can draw them with turtles and links. So let me, so instead of drawing the rivers in the patches, we can draw using, from the vector data, create turtles and links like the road. So let me set this up again. And now I'm going to draw them as turtles and links, right? Or here's drawing U.S. rivers in green. Maybe I can make this a little bit bigger here too. Or here, display elevation. Now that's bringing in a raster, right? And notice that happened here when you look at the code. Let's see if it's here. Display elevation. When we bring in our elevation, so this is bringing in a lot of different data sets. It's bringing in as vector files, cities, rivers, countries, and then the elevations brought in as a raster. And then to find our bounding area, it's finding the union of all of those. And notice when we say display elevation, you have a choice of painting to the patches, which are very low resolution, but on the elevation, instead of assigning it to the patches, there's this paint idea where it's painting it to the drawing layer. And the drawing layer in NetLogo is much higher resolution often than the patches. And in this particular model, it's 4 times for every patch, there's 4 pixels on the drawing layer. That's what that patch size means. So the drawing layer, and that changes, by the way, as I change this. So if I make that a little bit bigger, that patch size just went to 10.562, right? So now if I was to draw elevation again, that's at the resolution of the screen, not the patches. And now if we compare that to drawing on the patches, and when I do that, by the way, the patches are below the drawing layer, so I shouldn't see anything happen. I didn't see it change because the drawing layer is on top. So let me clear that again and display elevation in patches. So you can see that's the actual patches, and that's much lower resolution. Right? So this is a good place to kind of learn manipulating vectors and rasters in a very querying and how to paint them and display them. But you'll notice there's no simulation on this example. My cars would tell you, like, if you wanted water or a chemical going down the rivers, you would use cars on this river, right? If you're modeling, and Los Alamos has like 2, and in science in general, we have 2 general approaches for modeling transport, whether it's chemicals or light or mass or acoustics. Modeling it as a particle that you apply forces to, like a bullet, and you're putting wind on it, and with a dx and dy, or like David said, when you want to make sure you're having the conservations, that's where you're looking at patches or volumes and making sure that they're trading off with their neighbors. And if you want to be fancy at a dinner party and look smart, you call that Lagrangian versus Eulerian approaches. I call it turtles versus patches. But turtles approaches, is this fair, David? Turtles, if you're doing stuff with turtles,
Yeah,
is Lagrangian. If you're doing it with patches, it's Eulerian. If you're conserving the quantities like
yeah,
mass
that's fair, right?
Fair. And doesn't that make you
We
sound a
also
lot smarter?
do particle basis
You don't want to say
and continuous. Yeah, no, it's great.
because like there's a little bit of it's almost an oxymoron to have coding machismo, but like in the early days you had to be doing it in assembly and then C, and then you had to be really low. But JavaScript, like if you say you're a JavaScript developer, it used to have not a high pecking order, like you're not at the lowest level and in the middle, but frankly it's faster than Python, 40 times faster than Python, and approaching C in the browser, and it's deployable. Same thing with NetLogo. It sounds like it's because you learn it in 6th grade, you think it's a kid's tool, but it's not. At the leading edge scientific conferences with like computational social science, less so in physics, because physics still has that, it needs to be an MPI and C, and that's how I do it. They don't even accept MATLAB at some level, just because that's too high level. But I'll just say that if you don't want to use the word turtles because it makes you sound like you're in 6th grade, say Lagrangian. But I'm using Lagrangian approaches in NetLogo, and if you don't want to use patches, is also like cells. They're okay with that. So if you don't want, and that's just the social side of science. And just like if you go to an academic conference, you got to change your Excel graphs and charts so that it doesn't look like it was done in Excel and make it look like you did it in LaTeX, and it's just silly social stuff. But that stuff will change in the future.
Okay, Stephen, thank you. We're about finished with this session, and we're going to be going to our kind of a help you grow, different things to learn. And you're going to go into a different session, and it'll be from 2 to 2:50, and then you'll have another one that you'll pick a different session from 3 to 3:50. At the end of this whole entire thing, when you finish that and you've got a little bit of time, there is going to be an eval, a post eval of the whole thing, and we would like to have your opinions and your thoughts about what we did or could have done or whatever it was. So Stephen has put his email in and his phone number in the chat. So if you would like to get hold of him, then you can certainly do that. I will be sending that information to you as well by email. So I will also send you David's, so that if you want to get hold of them or you have questions, do not hesitate to do that. If you need some help and you don't know what to do or where to go, you are certainly welcome to contact me or consult, and we will find these fabulous people that you just got to listen to and help you get together with them. So do any of you have any other questions, or is there anything else we can help you with? You've been very patient and very good about at least answering the questions that we ask you. So David and Stephen, thank you so much.
Yeah, thanks for joining us.
Stephen, that was amazing. So, okay. Well, thank you. And I will be in touch with all of you students that we had. And I'm sure you too, David and Stephen, are going to have a few people who are going to get in touch with you.
Excellent. Thank you. This is my first year trying to do this virtual, so
yeah.
Thanks for sticking in it. And it's not as interactive as in person, but I think it kind of works.
Yes. Well, and it gives you the option to at least be able to get in touch with other people, and you've all learned different avenues to be able to do that lately. So, okay. Thank you.
Having them on their own computers instead of trying to get the lab computers to work, sometimes a little bit more convenient. Yeah.
Yeah. Okay. Thank you. Bye, Stephen. Bye, David.
Bye. Thanks.
Thank you. Bye.
Thank you.